Okay, this is the final video for your stats class. Hope you've enjoyed these as much as I've enjoyed making them. The topic today is going to be a little bit different because we're doing non-parametric tests. So these are tests that are based on frequencies, how often something shows up in your sample. Remember, a parameter is something that belongs to a population. Like in most cases, we've been talking about the mean and variance, or the mean and standard error, or things like that. But when you're just counting how many times something happens, you don't really average it. It's like when you take a vote, you don't average, you just count. And so it's very similar to that. And so for that reason, these are called non-parametric tests. These aren't very big in psychology. If you're doing a genetics class, you'll probably do chi-square, which is a version of this, because it talks about it's a way of testing for the frequency of a phenotype in a population or an experiment. Animal behavior, a lot of times does the animal do the behavior or not? Those are just situations in which we count it. I've got a couple of examples for you that we'll work through, so you can see exactly what the counting looks like. Anyway, I want to introduce you to how counting produces statistical distributions. This is a binomial distribution that I'm going to show you, and it means that there is only two possible outcomes, and you're counting how often each one happens. So that's like with a coin toss, you get heads or tails. It could be like how many people pass a test versus fail it. In a factory, in manufacturing, they do this to say how many observed pieces are working correctly or defective. And in all those cases, what you're doing is you pick one outcome, such as heads or pass, and you do a test on that. Okay, so other important things is when we're counting, we need these trials to be independent. A trial is something like a single coin toss. So if you do n of 50 trials, each time you toss the coin, you'll toss it 50 times, and each time the coin's going to land on heads or tails, regardless of what happened before it. The randomness is not affected by what happened before. That's what independent means. We don't have like traditional means and standard deviations, but we can calculate expected values and variance based on the probability of an outcome. So in a coin toss, for example, the probability is 0.5 for heads and 0.5 for tails, and then we can multiply by the number of trials to come up with an expected value for heads and a variance for heads. So anyway, I'm introducing this because I want you to see how non-parametric distributions works. We're going to do kind of a theoretical one here with coin tosses where the outcome that we're interested in is heads. So we're only choosing one of the outcomes to study here. Now, I'm going to show you 6 of these graphs. Each one is going to show you a number of trials. So this is one trial, and it's going to count the number of ways that you can get a certain number of heads. So this is telling us is that if you toss a coin one time, there's one way that you can get 0 heads. The coin can land on tails. There's one way that you can get 1 head. The coin can land on heads. So that's a very basic binomial distribution. Now, what I want to do is kind of show how this grows. We won't go all the way up to 50, but I'm going to wind up at 50 here. 2 coin tosses. It's possible to get 0 heads. How is that possible? Well, it has to land on tails both times. It's possible to get 1 head in 2 trials. That can happen in 2 ways. That number 2 means 2 ways. It could be heads and then tails, or tails and then heads. It's also possible to get 2 heads, and the only way that can happen is if you flip the coin twice and it lands on heads both times. Okay. So as this gets bigger and bigger, the principle is exactly the same. It's really not too hard to figure this out. I'll do one more just so you can see. Number of heads with 3 coin tosses. It's possible to get 0 if you flip the coin 3 times and it lands on tails each time. there are 3 ways that you can wind up getting one head. That can be heads, tails, 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 heads, tails, 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 heads. You should be able to, at this point, tell me how are you going to get 2 heads in a set of 3 coin tosses. Think about that. Well, there's 3 ways. Heads, heads, tails, heads, tails, heads, tails, heads, heads. Finally, there's only one way to get 3 heads, and that's if it lands on heads all 3 times. Okay, so we can continue doing that. I don't think we need to. I'll just show you what happens if you increase it to 4 and then to 5. Okay, now I said I wasn't going to go all the way up to 50. We're going to skip ahead to 50. So this is what that same graph looks like if you toss a coin 50 times. So N is 50 coin tosses or 50 trials. Now this it is possible to calculate an expected value, which is kind of like a mean. So that would be N times P. N here is 50 coin tosses, and P is 0.5. That's the probability of landing on heads. And then we can find the square root by N times P times the complement of P. So that would be N times P in this case, because P is 0.5. Okay, so I did that real quick. The expected value is 50 coin tosses, a 50-50 chance of it landing on heads. You'll wind up with 25 heads. That's what you would expect. And in fact, that's the highest thing here in this hypothetical distribution. The standard deviation would be the square root of 50 times 0.5 times 0.5. That standard deviation just tells us that we don't expect it to be exactly 25 every time, but 2/3 of the time it's going to fall within the standard deviation of that. All right, so that is an example of how distributions of categories can produce almost normal-like distributions. The test, and there are some tests you can do with this. The tests I'm going to show you are based on chi-square, and the reason we're going to do chi-square is because it's a little bit more flexible. Chi-square can be used in situations where you have 3 or 4 or 5 possible outcomes, rather than just tails and heads. So we're going to do 2 versions of this. Both cases we're testing for a distribution of frequencies across categories. This first one is going to be called a goodness of fit test, meaning that it tests whether your, it's kind of like one-way ANOVA, it's going to test whether your categories are distributed like you expect them to be distributed. The other is called a test of independence. It's a little bit more like a factorial ANOVA, and then it's got multiple categories of things. Okay, but they both have the exact same chi-square table and the exact same formula for chi-square. So what you'll see is that after having done factorial ANOVA, this is going to be really easy. So let me tell you about what I did. I've read that a lot of people are spending time on Duolingo trying to work on another language. I'm hoping to go to Morocco soon, and so I'm trying to brush up on my French. And I don't know any Arabic, so I thought I'd stick with one of the languages they know. There's this thing, there's a lot of, I don't know if you've never done Duolingo, it's just an online language learning thing. And they have several different activities and exercises. And this one drives me crazy because it gives you a weird sentence, a cat and a pizza, it's a phrase, and then you have to figure out which one of these is correct. And in this case, it's number 3. Now, I've been using Duolingo on and off for years. I try to brush up on a language before I go somewhere. So it's like working on Spanish for a while before I went to Cuba. And it started bothering me because whenever I got this exercise, the answer was almost always 1. And I was like, this should be random, right? I mean, you'd think the coders would go in there and say, choose one of these at random to be correct. And then now that I'm working on French, the same thing is happening. And so what's going on is that my expectations are different from my observations. Let me write how that works here. I would expect each number to be correct 1/3 of the time if these were randomly generated. Okay. What I observed is I counted this over 30 trials and found that the answer was number 1 almost half the time, 14 out of 30 times. So, and I'm like, is that weird? So this is exactly what the chi-square test does. This is the logic of the chi-square test. It says that under a null hypothesis, we would expect something. In my case, I would expect all these to be even. And then we observe something and see if it matches that expectation. When we say goodness of fit test, what we're saying is, does this fit our expectations? Now, let's run through the test real fast. In chi-square tests, we don't use notation for the hypotheses, so you can just write it out. I'm going to say the groups will have equal frequencies. My null hypothesis is that 1, 2, and 3 should be equally be the correct answer equal number of times. And the alternative is that they will have unequal frequencies. Now, it is possible to have a hypothesis where you don't expect them to be equal. For example, in class, we have a lot of biology majors, followed by neuroscience majors and psychology majors. So if I were to make a expectation, set an expectation for next semester, I would expect a distribution that's not equal across the majors. So I would write, I expect there to be 60% bio majors, 30% psych and neuroscience, something like that. So you can make that unequal if you want. Okay, critical value. Here the critical value is C minus 1. That C stands for columns, because as I'll show you in the next a couple pages down, we tend to put the data into columns. So I'll have answer 1, answer 2, answer 3, 3 columns, 2 degrees of freedom. You probably won't be surprised that there is a table for this. The table looks like this right here. For our study, we're going to do a 0.05. We have 2 degrees of freedom. We wind up with 5.991. Okay, so that's our chi-square distribution value. All right, I had to make a little room here. So our critical value is 5.991. For the calculations, the first thing we have to do is find our sample. So I did 30 trials. I did 10 lessons. Each lesson includes 3 of those. So what I found was 14 times the answer was 1, 6 times the answer was 2, 10 times the answer was 3. Now over here I'm using the word observed. That's the official vocabulary term here. These are observed values. We're also going to need to come up with expected values. Remember, an expected value is the probability times n, as I showed you back there with the coin toss. So in this case, my expected value is just something I came up with. I assumed they would be normally or randomly distributed, which would mean that I would expect 1/3 of the answers to be 1. 0.33 is 1/3 times 30, which is n, gives me 10. So I've got 3 categories and they're equal. I expect them to be 10. Okay? So that's how you find that. So now you can see I've got my columns here. I've got answer 1, observed 14, expected 10. Observed 6, expected 10. Observed 10, expected 10. All right. The formula for chi-square then uses the terms O and E. That's a sigma, meaning add up. This is observed minus expected squared over expected. Okay. And the sigma here says you add that up for each of our groups. So this thing right here we'll do 3 times and add them together. All right. So first time through, 14 minus 10 over 10 squared plus, there's my 6, 10. So 6 minus 10 squared over 10. And now 10 minus 10 squared over 10. All right, so that's just observed minus expected squared over expected for each column. And they're added together. When I did that, I came up with a 3.2 for my chi-square. And so for my decision, my test value of 3.2 is less than the critical value. So I do not reject the null hypothesis here. So even though it really feels weird to me, and I get mad at Duolingo for being unequal, it's not significant. Okay. As I said, there's actually 2 versions of this. I found this statistic that I wanted to test here about the graduation rates of NCAA Division I athletes, comparing men to women. Now, in this case, this is called a chi-square test of independence because we've got 2 categories here and 2 categories here. In these 2 categories, we're going to see if they operate independently of each other. Now, basically, what I'm going to start with is I would expect men and women to graduate at the same rate, barring no other information. I don't know that much about this. But then when I observed this and I saw this, it looked very different to me. Men were more likely to leave without a degree. Women are more likely to leave with a degree. Is that weird, or is that still the same ratio for men and the same ratio for women? Are they graduating at about the same rate? Well, to test that, we have to allow for just some sampling error and randomness, but it certainly doesn't look like it's going to be the same. All right, so for this hypothesis, I'm going to say males will graduate at the same rate as females. And then for the alternative, I'm going to say the groups will graduate at unequal rates. For my critical values here, I have C minus 1 times R minus 1. And again, that's going to be columns. Remember, I had males versus females. So right there, 2 minus 1. R's for rows. We had graduate or didn't graduate. So that's 2 minus 1. And 1 times 1 is 1. So our critical value here for 0.05 and 1 degree of freedom is 3.841. 3.841. All right. All right, so what I'm going to do for my observed values is I'm going to add some columns here. Earlier I just showed you what was going on inside the table, but this is a total. So this is all of the men, all of the women. Over here, these are all of the athletes that did not get a degree, and these are all of the athletes that did get a degree. And if I add up those 2 numbers, I get 3,291. If I add up those 2 numbers, I get 3,291. All right, and again, this is observed. The next thing we have to do is figure out the expected value. Now, the expected value here requires a quick formula where you multiply the total for a row and the total for a column for each of the 4 categories. And they get divided by n. I'm going to show you each one here real slow. The first one up here in the top left, I need to find the expected value of men with no degree. And to do that, I'm going to get the top row, 1784, left column, 2332, divided by the total number, 3291. And I put that number right here. That gives me 1,264.14. All right, now I'm going to move down to this row. This is the expected value for the bottom row left column. The bottom row has an N of 1507. Left column is 2332. And it has an N of 3291. So the expected value there is 1,067.86. Okay. All right, for the top row right column, 1784 times 959 divided by 3291, 519.86. And then the bottom row right column, that is 1507 from right there times 959 right there divided by 3291. That gave me 439.14. Chi-square. Notice it's the exact same formula. This time we'll do that for 4 different categories. Okay, so the very first one, so I have the men with no degree. 1343 is observed. 1264.14 is expected. Put that down there. For men who graduated, it's 989 minus 1067.86 squared over 1067.86. 441 minus 519.86 squared over 519.86. Oops, I did that out of order, but I think you can figure it out. Okay, so by the time I got through all of these, I racked up a pretty big chi-square number there. Chi-square of 36.87. I got a little freaked out and I went and used some software to check my work, and that was correct because that's a very big chi-square. The decision here is that our chi-square value is greater than the critical value, so we can reject the null hypothesis. Now, what that means is that men and women are not graduating at the same rate. If I want to understand more about that, I can just go look at the ratios. I see that men are graduating at a lower rate. Fewer than half of the men are graduating with degrees, whereas more than half of the women have graduated with degrees. And that's a significant difference, so the ratio's different there. All right, well, that's the last test I'm going to show you, and it's the last test I will make you learn.